Welcome to the deep dive. Today, we're going to be taking a deep dive into a topic that you specifically requested.
Oh, cool.
Combinatorics on words.
Okay.
You sent over a Wikipedia entry, and I have to admit that the title alone
Yeah.
piqued my curiosity.
It's a good one.
It sounds a little intimidating, but I have a
Yeah.
feeling it's going to be one of those unexpectedly fascinating rabbit holes.
It definitely is. It might sound like something straight out of a math textbook, but it's surprisingly relevant to everyday life,
Okay.
especially given your interest in computer science.
So before we get lost in the jargon,
Yeah.
can you break it down for us? What exactly is combinatorics on words?
Well, you can think of it as the mathematics of language and patterns, but instead of focusing on words in the traditional sense,
Okay.
we're looking at any sequence of symbols, letters, numbers, even musical notes.
Interesting.
It's all about exploring how these sequences behave, the properties they possess, and the fascinating structures that emerge.
So it's more about the arrangement and patterns of symbols rather than the meaning of the words themselves.
Exactly. It's like taking language apart and analyzing its building blocks.
Okay.
For instance, even a simple system like binary code with
Right.
just zeros and ones can create an incredible variety of sequences, each with its own unique properties.
That makes sense. And I can already see the connection to computer science, binary code, being the foundation of how computers process information.
Absolutely. That's actually one of the key areas where combinatorics on words comes into play.
Okay.
By studying binary sequences, we can design more efficient algorithms, develop better compression techniques, and even create more secure encryption methods.
So it's not just theoretical. It has real-world applications that impact how our technology works.
Exactly.
That's pretty cool. Now, the Wikipedia entry you sent over breaks combinatorics on words down into 4 subcategories:
Okay.
binary sequences, formal languages, permutation patterns, and problems on strings.
Yes.
Can we unpack those a bit?
Definitely. Each subcategory delves into a specific aspect of how we analyze and manipulate sequences of symbols.
Okay.
Let's start with formal languages, since that directly relates to your interest in computer science.
Right.
It deals with defining the rules for creating grammatically correct sequences.
Oh.
Like the syntax of a programming language.
So it's like the grammar police for computer code,
Yeah.
making sure everything is structured correctly.
You could say that. Formal languages helps us define what constitutes a valid program in a particular language,
Right.
ensuring that the computer understands our instructions correctly.
Okay. That's a really interesting way to think about it. And I can see how that ties into binary sequences, which we talked about earlier, since those are essentially the words that computers understand.
Huh.
What about these other subcategories, permutation patterns and problems on strings?
Well, permutation patterns focus on analyzing the different ways you can order elements within a sequence.
Okay.
Imagine shuffling a deck of cards.
Right.
Each arrangement is a different permutation. This has applications in areas like algorithm design and optimization.
So it's about finding the most efficient ways to arrange things.
Exactly. And then we have problems on strings, which is a broader category that encompasses a wide range of challenges related to manipulating and analyzing sequences.
Okay.
One example is the longest common subsequence problem.
Okay.
Imagine you have 2 strings of DNA.
Right.
This problem asks you to find the longest sequence of genetic code that's shared between them.
That sounds like it would have huge implications for genetic research.
Yeah.
I'm starting to see just how widely applicable this field really is.
Yeah.
But before we dive deeper into those applications,
Sure.
I want to touch on some of the specific concepts mentioned on the Wikipedia page.
Okay.
Things like square-free words and the necklace problem.
Yeah.
They sound intriguing, but I have no idea what they are.
They do have catchy names, don't they? Let's start with square-free words. A square-free word is a sequence that doesn't contain any consecutive repeated blocks. For example, the word banana wouldn't be square-free because it has the repeated block nah twice.
Interesting.
These types of words have interesting applications in areas like coding theory and cryptography.
So it's about creating sequences that avoid repetition.
Right.
Why is that important for coding and cryptography?
Well, in coding theory, square-free words can be used to prevent errors in data transmission.
Okay.
Imagine sending a message over a noisy channel. Using square-free codes can make the message more robust to errors.
That makes sense. If there's repetition and a part gets garbled, it would be harder to reconstruct the original message.
Right.
So by avoiding repetition, you're essentially building in error correction mechanisms.
Yeah.
What about the necklace problem? It sounds a bit less technical,
Yeah.
but I'm guessing there's more to it than meets the eye.
Definitely. The necklace problem involves dividing a necklace with beads of different colors
Okay.
fairly among a certain number of people, ensuring each person receives the same number of beads of each color. It might sound simple, but the mathematical solution involves analyzing the possible arrangements of beads,
Right.
which ties back into combinatorics on words.
Okay, I'm starting to see how something that sounds whimsical, like dividing a necklace,
Mm-hmm.
can actually involve complex mathematical concepts.
Precisely.
Yeah.
And that's one of the things that makes combinatorics on words so fascinating.
Yeah.
It connects seemingly disparate ideas and reveals the hidden structures and patterns beneath the surface. Now, there's another concept mentioned on that Wikipedia page that I think you'll find particularly interesting given your interest in computer science.
All right, let's hear it.
Automatic groups.
Automatic groups.
Hmm.
Okay.
Mhm.
You mentioned earlier that this field helps us understand how computers process information.
Right.
How do automatic groups fit into that?
Imagine you have a set of rules for generating sequences, much like the grammar rules we talked about earlier.
Yeah.
An automatic group uses these rules to create a group, which is a mathematical structure with specific properties. These groups can then be used to study algorithms and even solve problems related to geometric objects.
So it's like using math to understand the underlying structure of algorithms.
Yes, and one of the most famous examples of this is the Rubik's Cube.
Oh, wow.
Believe it or not, automatic groups can be used to analyze the possible moves of the Rubik's Cube and even find the most efficient solutions.
Wow, that's pretty mind-boggling. We're talking about using mathematical groups to solve a puzzle.
Exactly. And that's just scratching the surface of what automatic groups can do.
Wow.
They have applications in fields like cryptography, computational linguistics, and even theoretical physics.
Okay.
It's a really fascinating area of research.
This is already blowing my mind, and we've only just begun. I'm starting to see how combinatorics on words isn't just some abstract mathematical theory. It has real-world implications that touch on so many different areas.
That's what makes it so exciting.
Yeah.
It's this hidden language that helps us understand the world around us, from the structure of our DNA to the algorithms that run our computers. And what's even more amazing is that it's not just about analyzing existing patterns, it also gives us tools to create new ones.
Okay, I'm definitely hooked. Before we move on to those applications, I think it's worth pausing here to let all of this sink in. We've covered a lot of ground, from the basic definition of combinatorics on words to some of its more intricate concepts. But don't worry, we're just getting started. When we come back, we'll explore how these ideas are being used to solve real-world problems in fields like biology, linguistics, and even cryptography.
So, we've been talking a lot about the theoretical side of combinatorics on words,
Right.
but I think it's really important to showcase how these concepts are actually being applied to solve real-world problems.
You're absolutely right. It's all well and good to talk about these abstract mathematical ideas,
Yeah.
but I'm much more interested in seeing how they actually make a difference in fields like biology or linguistics.
Well, let's start with biology, because I think you'll find this particularly fascinating.
Okay.
Remember how we talked about DNA being like a word with
Yeah.
its four-letter alphabet
Right,
of
yeah.
A, G, C, and T?
Yes. It's amazing to think that our genetic code is essentially a sequence of symbols, just like the ones we've been discussing.
Exactly, and that's where combinatorics on words comes in.
Okay.
By applying these principles,
Yeah.
scientists can analyze DNA sequences, identify patterns, and even pinpoint specific gene mutations responsible for certain diseases.
So it's like using math to decode the secrets of life itself. Can you give me a specific example of how this is being used?
Absolutely. One groundbreaking application was the identification of the gene mutation responsible for cystic fibrosis.
Okay.
Researchers used combinatorics on words to analyze DNA sequences from patients with the disease
Right.
and were able to pinpoint the exact mutation causing the problem.
Wow.
This discovery paved the way for the development of new diagnostic tools and even potential gene therapies.
Wow, that's incredible. So we're not just talking about theoretical possibilities here. This is actually leading to real breakthroughs in medical research.
Precisely. And it's not just limited to cystic fibrosis.
Right.
Combinatorics on words is being used to study a wide range of genetic disorders, understand evolutionary relationships between species, and even develop new drugs based on genetic patterns.
It's amazing to think that a field that started with analyzing patterns in words is now helping us unlock the mysteries of our own biology.
Okay.
You also mentioned linguistics as another area where these concepts are being applied. Can you elaborate on that?
Of course. Remember how we discussed formal languages and how they relate to the grammar of computer code?
Yes.
Well, the same principles can be applied to human languages.
So we can use math to analyze the structure and patterns of the languages we speak every day.
Exactly. Combinatorics on words can help us understand how words are formed, how sentences are structured, and even how languages evolve over time.
So could we use this to, say, trace the origins of different languages
Uh-huh.
or predict how they might change in the future?
Those are some of the exciting possibilities.
Yeah.
Researchers are using these techniques to analyze ancient texts, reconstruct proto-languages, and even model how language might evolve based on current trends.
That's fascinating. It's like having a mathematical time machine for language.
Yeah.
You know, it's funny. At the beginning of this episode, I was a little intimidated by the term combinatorics on words,
Yeah.
but now I'm seeing patterns and connections everywhere.
That's the beauty of this field.
Yeah.
It opens your eyes to the hidden structures that underpin so much of our world. Now, there's one more application I want to touch on, and I think it might pique your interest given your tech background.
Okay.
Cryptography.
Cryptography. I was hoping you'd bring that up.
Yeah.
It's always seemed like a mysterious and somewhat intimidating field.
It can be,
Yeah.
but at its core, it's all about using math to secure information and communications.
Right.
And combinatorics on words plays a crucial role in that.
Can you give me an example of how that works?
Well, one important aspect of cryptography is creating strong encryption keys.
Uh-huh.
These keys are essentially sequences of symbols
Right.
that are used to scramble and unscramble messages.
So it's like having a secret code that only the sender and receiver know.
Exactly. And combinatorics on words provides the tools for generating these keys, ensuring they are random, unpredictable, and difficult to crack.
So the next time I'm sending a top secret message, I should brush up on my combinatorics on words.
It couldn't hurt. But seriously,
Yeah.
it's fascinating how a field that started by analyzing simple patterns in words has become essential for protecting sensitive data in our increasingly digital world.
You know what's really striking me is how this field seems to bridge the gap between pure mathematics and real-world applications.
Yeah.
It's not just about solving equations. It's about using those equations to understand and manipulate the world around us.
That's a great observation. And it speaks to the power of mathematics as a tool for discovery and innovation.
Right.
It's not just an abstract pursuit. It's a key to unlocking the secrets of our universe and shaping the future.
I'm really starting to see that. Now, before we wrap up, there's one more concept from the Wikipedia page that I wanted to touch on.
Okay.
Avoidability in words.
Okay.
Can you explain what that means and why it's important?
Of course. Avoidability in words refers to whether certain patterns can be avoided entirely when constructing sequences.
Okay.
For
Yeah.
instance, can we create an infinitely long sequence of zeros and ones that never contains the pattern 000?
So it's like playing a game of pattern avoidance with words.
Yeah?
Why is that relevant to the real world?
It might seem abstract, but it has surprising applications in areas like data compression and even game theory.
Okay.
In data compression, for example, finding ways to avoid redundant patterns can lead to more efficient storage and transmission of information.
So the algorithms that compress files on my computer might be using principles of avoidability in words.
They very well could be.
Yeah.
And that's just one example.
Yeah.
It's amazing how something that seems purely theoretical can have such a direct impact on the technology we use every day.
I have to admit that before this deep dive, I never would have guessed that the study of patterns in words could be so multifaceted and impactful.
Right.
It's really opened my eyes to a whole new way of looking at the world.
That's what we aim for.
Yeah.
And what's even more exciting is that this field is constantly evolving with new discoveries and applications emerging all the time.
I can't wait to see what the future holds for combinatorics on words. But before we get ahead of ourselves, I think we should wrap up this part of our discussion and give our listener a chance to process all of this amazing information.
Okay.
We've covered a lot of ground, from the basic definition of combinatorics on words to its applications in fields like biology, linguistics, and cryptography. But don't worry, we're not done yet. When we come back, we'll explore some final thoughts and leave you with some provocative questions to ponder. So what's truly fascinating about this deep dive into combinatorics on words?
What's that?
It's made me realize that patterns and sequences aren't just abstract mathematical concepts. They're woven into the very fabric of our reality.
That's a great way to put it. Whether we're talking about the arrangement of nucleotides in our DNA, the structure of sentences in a book, or even the algorithms that power our smartphones,
Yeah.
it all comes back to these fundamental principles of combinatorics on words.
It's like we've uncovered this hidden language that permeates every aspect of our world.
Mm,
And the more we explore it,
right.
the more connections and possibilities we discover.
Exactly. It's about seeing the world through a new lens, recognizing the intricate interplay of patterns and sequences that often go unnoticed.
So for our listener out there who's been on this journey with us, what's the key takeaway? What should they walk away pondering?
I think the most important takeaway is this. Combinatorics on words isn't just a niche area of mathematics. It's
Yeah.
a powerful tool for understanding and manipulating information.
Right.
It has far-reaching implications for fields that impact our daily lives, from the technology we use to the very essence of who we are as biological beings.
It's really a testament to the interconnectedness of knowledge and the surprising ways in which seemingly abstract ideas can have real-world impact.
Absolutely. And I think it also highlights the importance of curiosity and exploration.
Right.
You never know where a deep dive into a seemingly obscure topic might lead you.
That's so true. Now, before we sign off, I'd love to leave our listener with a final thought-provoking question. We've talked a lot about how combinatorics on words helps us analyze existing patterns.
Okay.
But what about the patterns we create ourselves?
No, that's a really interesting question.
When we write a poem,
Hmm.
compose a piece of music, or even design a building, are we, in a sense, engaging in our own form of combinatorics on words?
That's a great point. Are we intuitively tapping into these mathematical principles without even realizing it? I think I'll be mulling that over for quite some time.
I suspect we all do, to some extent.
Mhm.
It speaks to the inherent human desire to create order,
Yeah.
find meaning, and express ourselves through patterns and arrangements.
Well said.
To our listener, we encourage you to keep exploring the fascinating world of combinatorics on words. Who knows? You might just stumble upon the next groundbreaking discovery or application. Thanks for joining us on this deep dive. Until next time, keep those minds curious and those questions flowing.